All right, good morning. Hold on a second. Trying to figure out why I can't get to my control panel. All right, everyone. Hope you had a good weekend. We are going to be doing 8.2 series today, and after some thought and talking with some of your classmates, I've decided to make exam 3 a take-home exam. I'm going to send it out later today. There is a possibility I get delayed till tomorrow morning on that, but I'm going to try for today. It'll be due on the 17th, which is Sunday, this upcoming Sunday. My plan is to grade those on Sunday. And that way, if anyone has any concerns about their grade in the class, the last day to drop this class is the 18th, which would be the following day. So you would have, basically, you would know going into the final, like where you stand. Does that make sense? Okay. Now, in terms of a take-home exam, it's going to be a little different than just like homework type problems. They're going to require a little bit more from you in terms of, you know how I said I would give you an exam where all you do is set up the integrals? Well, these, you're going to have to take them all the way, but I will specify whether or not I want you to use technology to do that or not. Some of them I'll say, you know, do it by hand. And then other ones I'll say, use Symbolab, use Wolfram Alpha, and you can get the answer that way. All right. So I'll send out the test. And then if you have any questions over the test, you can always meet me in my office hours. We can talk about it on Wednesday. At least by the time we get to class on Wednesday, you know, have looked through the exam. Do not wait till Saturday at, you know, 8 o'clock in the evening to start the test and look at it for the first time, because it is going to be take home. It's going to take you a little bit longer than it would be if you were in class doing it. Okay. Now, the reason I'm doing take home is really because we need that day for lecture instead of a test. It's because, you know, we just don't have enough time. I'm trying to get through the material. So when I send the exam out, it'll have, you know, more detailed instructions on it. All right. Okay, we're going to start 8.2 today, series, and I have a ton of notes here to get through. So let's get started. All right, so we are going to start out 8.2 series with some definitions and then some examples to kind of get us thinking about it. So first we need to know what sigma notation is. And a lot of you have seen sigma notation, a lot of you have not. So just to remind you, the Greek letter S, capital S, is written this way, sigma. And in mathematics, we use this symbol to help us write repeated sums in a more condensed fashion. So for example, if we wanted to write 1 plus 4 plus 9 plus 16 plus 25 plus 36 all the way to 100, what we could do instead is realize this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way till we get out to, what would this be out here, 10 squared, right? So instead of writing all that down, I realized there's a pattern of just squaring the input each time, and the numbers I'm plugging in are going to be the integers, the positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 10. So what we do is we write the sigma. On the bottom, we put n equals 1. On the top, we put 10. This tells you where to start, and this tells you where to stop. And then this right here is the actual formula that we're using for the sum. So if I start with 1, I square 1 squared, that's my first one. Then I put plus, and now I let n go to 2, and do 2 squared, and that's 4. And then plus, and 3, and then 4, and then 5, and then 6, and we stop when we get to 10, which would be 100, right? 10 squared. Sometimes students ask me, okay, there's a notation we use for, this is like repeating addition over and over. Students will ask me, is there a formula or a notation for if you wanted to do, instead of 1 plus 4 plus 9. How about 1 times 4 times 9 times 16 times 25? And we actually do have a symbol. We would use the capital letter P, which is pi, a large pi, and then we would do n equals 1 to 10, and then n squared. And that would mean 1 squared times 2 squared times 3 squared times 4 squared. But we're not going to use that in this class. I'm just telling you there is a way to do it. We use pi because P for product, and we use the Greek letter S for sum, right? That makes sense? All right, so that's the notation for sigma. We start at n equals 1. Like initially when we're first learning sigma, we always start with n equals 1, but n can actually start anywhere we want it to start. It just needs to go up by 1 integer each time. So we could start this sum at 4 if we wanted, n equals 4 to 10. It just needs to jump by 1 each time we go up. All right. Questions on that? Now, what I gave you here is an example of a finite sum because we stopped at 100. But what if we wanted to go forever? You know, 1 plus 4 plus 9 and just keep doing that forever. The notation would change just slightly. Instead of stopping and putting a 10 here, we would put an infinity there, and that would mean it goes forever. That would be what's referred to as an infinite sum. Okay? Questions on the notation? The n squared in here is like the formula. In fact, you could look at the n squared as almost like a sequence. Think about what we've learned so far. If I gave you the sequence a sub n equals n squared, this would create the sequence of numbers 1, 4, 9, 16, 25, right? Like that. It would go forever. And if I wanted to add them up, then all I'm doing is throwing a sigma in front of that sequence formula, right? That's all I'm doing. So that n squared here, generally speaking, could just be our a sub n formula for a sequence. All right, so what is a series? A series is simply the sum of a sequence. And we usually call it S, capital S, for sum, okay? So if we take a finite sequence, right? So if I give you a sequence that has a finite number of numbers in it, a sub 1, a sub 2, a sub 3, and I stop that sequence at a sub m, then the series for that sequence, right? The series for that sequence would be capital S equals, and then you just add up all the numbers. But see, you're going to stop, aren't you? Because it's finite, you're going to stop somewhere. So would you all agree with the idea that if I give you a finite sequence and ask you for the series, you're going to get a finite answer? Like your answer is going to be a number, guaranteed, every time. Finite sequence, finite sum. We're not interested in that in this class, okay? Finite sums are not interesting. We're interested in what happens if you take an infinite sequence.
Professor.
Yes.
So sorry, really quick. Hunter's trying to get
ahead.
inside the class.
You're what?
Hunter is trying to get inside the class. You can go ahead and let him in.
Oh, I don't know why he's not in. Oh, he must have been like the first one here.
Sorry about that.
No, I'm glad you let me know. I was kind of wondering where he was. We'll let him come in. Hey, Hunter, sorry about that. It didn't let me know someone was in the waiting room. My fault.
It's cool. I figured I should somebody after a few minutes just to make sure
Yeah.
it wasn't crazy.
Thank you. All right, so we are interested if you have an infinite sequence, right? A list of numbers that goes forever. Then if you start adding those up forever, what's the sum? All right, and we talked about this, a class or two ago. We said, sometimes these sums would become bigger and bigger and bigger and just become infinitely large, but then other times, maybe it's not infinite. All right, So we are going to be trying to investigate this, and we're going to be asking, does this infinite sum, converge to a number, or does it not? Right? So here's a first example, some first examples. So the first one we're going to look at is a sub n equals n. Okay, that's a sequence from last time. That's just the sequence 1, 2, 3, 4, 5 forever, right? So what about the sum of these numbers? The sum of 1, 2, 3, 4, 5 forever. What is it? What's happening to it? I mean, it just keeps getting bigger and bigger and bigger, doesn't it? Right? The more numbers you add on, the larger the sum gets, and that sum should become infinite, right? It should become infinitely large. So I want us to try and visualize this right now. Visualize what's happening. So I have an animation here for this. Come on. All right. So let me make sense out of the thing. Let me try and make sense out of what you're looking at here. On the left side in black, you are looking at the sequence of numbers. Remember, we said a sequence can be visualized as a bunch of dots. So let's write out this sequence. The sequence is 1 over n. That's what we're looking at, 1 over n. So that sequence is the sequence, let's see, 1, 1/2, 1/3, 1/4, and it keeps going forever and ever, right? So on the left-hand side here, notice the first number is a 1, and that is how tall this point is, right? That's how tall it is. It's 1 unit high. The next number is a 1/2. That's this one right here. That's how tall that's how high up that point is. This one is 1/3, 1/4, 1/5, 1/6. All right. Now let me try and explain what's happening on the right-hand side. On the right-hand side, you're not looking at this sequence anymore. What you're looking at is the sum of the sequence. So when I go here to 1, what this 1 means right here is that I'm just taking the first, I'm going to write it this way. So when I say what's S sub 1, okay, that's 1 being plugged in here. That means I'm just summing up the first number of the sequence. So if I just take the first number, 1, I get 1, don't I? Now, if I say, what's the second number in the sum, that means I'm going to add the first 2 together. So what would 1 plus a 1/2 be? 1.5. That's how tall this point is. Do you see that? Now, if I do S sub 3, that's going to be the first one plus the second one plus the third one together. So that'd be 1 plus a 1/2 plus a 1/3. So you'd have to get a common denominator and add those up. That's how tall this one is. Y'all understanding this? Do y'all see that if I keep doing this, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, do you all see that I'm actually creating a new sequence of numbers? It's a new sequence. The new sequence is this number, right? S sub 1. Not a good color. S sub 1, and then I have S sub 2, then S sub 3, then S sub 4, right? This is a new sequence, but it has a different meaning, right? This new sequence represents the sum of this sequence, right? Up to a certain point. So the 10th term in this sequence, the 10th number in this sequence, S sub 10, would be the first 10 of these added up, right? And so look at the picture of this. So what I'm going to do now is I'm going to start showing you more of the sequence. So here we go. On the left-hand side, these are the ones we're adding up. Okay, so I'm adding more and more of these together. Notice on the left side, I need to clear all this shit out of here. Notice on the left side over here, what is the sequence headed towards? 0, right? Everyone see it? And we knew that already because this is the sequence a sub n equals 1 over n. And I know that 1 over n converges to 0 because if I just take the limit, 1 over infinity goes to 0. So yes, of course, the sequence is headed to 0 over here. But what is the sum sequence doing? Look what it's doing. Look at the number here as I go further and further out. Look what happens to this number. It's at 4.8, right? These are getting bigger and bigger and bigger and bigger, right? This thing's getting bigger. And let me get more points. Now we're above 5. Now we're above 6. I'm going to really start to slow my computer down here. Okay. Look at the shape of this sequence over here. The shape of this sequence, that sequence is headed off to infinity. Doesn't it at least look like that? Which makes us believe that maybe the sum of that sequence is infinite, right? If I take the sum n equals 1 to infinity of 1 over n, it looks like this is headed to infinity. Now, don't confuse that. The sequence itself, 1 over n, that goes to 0, right? The sequence goes to 0, but the sum of the sequence, the infinite sum of the sequence, looks like it's going to infinity. This is still not completely rock solid clear to us whether or not it is or is not going to go to infinity, but it looks like it is, right? It at least looks like it is. Questions there?
So why is that the case that those two can shift so dramatically? Like is that for everything, or is it just
No,
kind of how it works?
It's not for everything. Let's look at another example. All right, let's look at another one. Okay, so let's go back. And what was my second one? Sorry, let's do 1 over n cubed. Okay, so if I change this to 1 over n cubed. All right. Oops, I didn't want to do that. Okay, let's first again look at the left side. The left side is just the sequence. So we're doing a sub n equals 1 over n cubed. Again, we know that goes to 0, right? Fixed over infinity, that sequence goes to 0. But what about the sum of that sequence? What does it do, right? That's the question. What is it doing? So let's just look at it over here. Okay, here it is. Let's start going further and further out. Well, it was growing, wasn't it? It was growing. But does that look a little more asymptotic to you? Like almost like there's it almost looks like the sequence on the right is bounded above, doesn't it? It looks like it might be bounded above. But the sequence on the left, right, the things we're adding up, those are definitely going to 0. But the one on the right, when we're adding them up, doesn't quite look as infinite as the previous example, does it? So again, we don't have a question. We don't have a question. We don't know for sure, but I'm kind of wondering, maybe this is finite, right? Maybe that's finite. I don't know. I don't know. And this is the challenge for us, is that if I give you a sequence and then ask you to find its series, can you figure out whether or not you're getting a finite answer or if you're getting something infinite? That is the goal, all right? To figure that out, at least the goal for the next
Can you repeat that one more time?
Okay, so
actually, can you write it? Can you write it?
Well, it's going to be in the notes.
Gotcha, cool.
When I go back to the notes, okay? So where am I? So I'm in my notes. Okay, let me back this up so I don't freak my computer out. All right. So the ones we looked at, notice that each term gets smaller and smaller, but what about the sum? It looked infinite, right? This one, the second one we looked at, each term got smaller, right? We knew it went to 0 really fast, but the sum kind of looked like it might be finite, all right? So the big challenge, what we are seeing is that some series sum to be infinite and some do not, all right? They seem to converge to a number. But can we tell by just looking at the sequence? By just looking at the sequence, is that enough for you to tell whether or not the sum of this sequence is going to converge or diverge. All right, that's kind of like, wouldn't it be nice if we could just look at the sequence and be like, oh yeah, if we add these up, it's going to be finite, or look at the sequence, go, oh, if we add these up, it'll be infinite. Wouldn't it be nice if we could just look at the sequence itself? Yeah, right. It's not going to be that easy. All right. This is the hard part about series. There is not an easy check. All right. There's not an easy way to do it. In fact, we're going to have to develop a bunch of methods to do it. And these are what are called our series tests. It's what we will use to figure out whether or not a series converges or diverges. And just as a kind of spoiler, these are in our formula sheets. Oh, where are they? Where the heck are they? I thought I put them in here. Okay, I'll get to them later. You know what? I'll get to them now. Give me a second. These are in Canvas, of course, for you. I kind of wanted this for today. I thought they were there.
Quick question while you're
Yep.
fetching this. So I was looking at the schedule and it says that the exam 3 is this Wednesday. Is that still the case since
Yeah,
we
sorry,
haven't completed the bits that are before it?
Yeah, so that I announced at the beginning of class that exam 3 is going to be a take-home exam that will be sent out today.
Okay. When
Yeah.
is it due?
Sunday at 11 a.m.
Gotcha. What is the difference with a take-home exam versus the one that we normally do? Besides,
Let me send it out. You'll take a look at it. It'll have instructions, and then we can talk about it on Wednesday if there are questions about what the expectations are. I'll lay it out
gotcha. Cool.
in the test, like what I expect, but you will be required to use some technology to get final answers for things like Symbolab or Wolfram Alpha or something like that.
Is it cool to use Desmos?
Yeah, if you want to do integrals that way, you can.
I was just thinking for the graphs on some of them because
you might. Yeah,
I like it a lot more
good.
than the graphing calculator.
Yeah, absolutely. Yep. Yeah, so the problems will be a little bit harder than what I would do in like a face-to-face test, but they'll all be within what I would consider reason. All right. I don't know why this is so slow. Let me see here. Formulas. All right. So here they are. So these are the tests that we are going to have to learn in order to figure out whether or not certain series converge or diverge. All right. So we got to go through all it. We got to learn all this. All right. We got to learn all this. So does that answer, well, Lewis? I don't see Lewis, but I think that addresses his be wanting to say, write down what I was saying. I think the notes make that clear. I hope. There is not going to be an easy check. All right. So let me get to some notation and language. All right. Very important that we understand this stuff. All right. If you're given an infinite series, okay, so you're given this notation, sum n equals 1 to infinity. A sub n is our sequence formula within the series. This just means you're going to add up A1 plus A2 plus A3 forever, right? That's notation for a series, for an infinite series. Our first definition here is what's called the nth partial sum. The nth partial sum is denoted S, capital S subscript n. And what it means is you're going to take this infinite series, but instead of letting it go forever, you're going to stop it at n. So you're going to create a finite series that goes from the first term to the nth term. That is called the nth partial sum. So if we kind of think back again, what does S sub 1 mean? It meant you added just the first number in the sequence. S sub 2 meant you added the first 2. S sub 3 meant you added the first 3. S sub 4, the first 4, right? So S sub n would mean you add up the first n. And I already told you this. Notice that this now creates a new list of numbers, right? I know that each one of these is a number. The reason I know each one of these is a number, not infinite, is because the sum I'm doing is finite, right? If I just take one number, that's a number. If I add 2 numbers together, it's a number. If I add 3 numbers, it's a number. If I add 4 numbers, it's a number, right? So I know S sub 1, S sub 2, S sub 3, S sub 4, S sub 5, keep going, is just a list of numbers. And that list of numbers is a new sequence. And the question is, does that sequence converge, right? Does it converge? And when I say it, I'm talking about this sequence. I'm not talking about the original sequence. The original sequence is where I got my formula from of what things are being added up. This sequence is actually a sequence of the sums, the partial sums.
Question.
So, yes.
If the sequence itself like goes to infinity, would it be reasonable to assume that the series, like this sum of them, would also probably go to infinity?
What do you think?
It seems reasonable that if my values that I'm adding together are just getting infinitely large, that their sum would also be getting infinitely large, wouldn't it?
So you're saying if our sequence becomes infinite, right? Like becomes big. A good example of that would be, let's say, a sub n equals n, right?
Yeah.
So if you take the limit of n goes to infinity of this, obviously that becomes infinite, right?
Yeah, it just goes off.
So you're saying if that's true, then the sum of that sequence, right? The sum, the infinite sum of that should also go to infinity. That's your kind of conjecture, right?
Yeah.
Does that make sense to everyone that should be the case? If the things you're adding up are getting bigger and bigger and bigger, right? Then as you keep adding more, the sum should get bigger and bigger and bigger.
I have a question.
Yes.
I could be wrong, but because I know last time when you covered, it was adding 1/10 plus 1/100th plus 1/1000 and continuing on. Would that be an example of something that doesn't infinitely grow?
That does not get bigger, correct?
Right. Would that apply to like this situation here?
Well, what Hunter's saying is, what if the thing that we're using grows, like gets really big, not really small, but really big? Hunter's saying that if we add them up, it should get big. Look at this sequence. This is the sequence 1, 2, 3, 4, right? That's the sequence, right? And so the series of this one, these are two, this is like in general, and then this is if one particular example. If we just take this sum, this means 1 plus 2 plus 3 plus 4. What Hunter is saying is that if we know the sequence gets bigger and becomes infinite, then when we add them up, each one of these gets bigger, then the sum should be infinite as well. I think that's a reasonable idea. But it doesn't, here's the thing, it doesn't even have to go, the original sequence here doesn't even have to be getting infinite, okay, for this to be true. We only need it to not be going to 0. If this sequence, now I'm going to give you this formally in a minute, okay? I'm going to give you this formally in a second. But if we have a sequence that goes to something other than 0, then the series will diverge. It will not be a finite sum. But let me get to that. We'll progress through it. Good question, though. Okay, so we have the idea of an nth partial sum. We've got this new sequence of numbers that represent the sums, and we want to know, does this converge? Which means that we have to take the limit as n goes to infinity, right? We need to see if we can take the limit as n goes to infinity of this.
Of the original a sub n?
No, not the original, of this new sequence, right? We've created a new sequence.
But wouldn't the limit of the regular sequences is not approaching 0, despite, you know, a sub n cubed, and the other one, I think it's a sub n plus 1. Doesn't that like have that term in, or like, because you just said that the original sequence doesn't need to go all the way to whatever infinity, as long as it just doesn't go to 0.
Yeah, but hold off on that idea. I want to formally like say that. Okay, right now we're just saying, if I give you a sequence, right, a sub n, right, we can start looking at these sums of this, and that creates a new sequence, s sub n, right? And we want to know if that s sub n converges, which means we need to find the limit as n goes to infinity of that s sub n. Let's not look at specific examples or cases or anything. This is just generally speaking, like the concept is this new sequence. We want to figure out what it's headed to by taking its limit. If this limit exists, then that's the sum. The sum, capital S, will be equal to the limit of that new sequence. I have bad news though. It's very difficult in general for us to find a formula for the new sequence, right? Because we start out with the sequence I give you, right? This is given. And then from this, you're going to generate a new sequence, right? A new sequence. This is hard to find in general. And if you can't find it, you can't take the limit, because you need the sequence, the formula for this sequence in order to find the limit and let n go to infinity. It becomes very problematic. Let's clarify. Given a series, right, an infinite series, we're going to let S sub n be the nth partial sum. So we're only going to look at the sum of the first n terms. If that new sequence, right, that we create converges to S, so if we can take a limit of it and it goes to a finite number S, then we will say the original series is convergent and it converges to S. Otherwise, it's what we call divergence. Or yeah, otherwise we say it diverges. Okay, so right now everything should be very abstract because we haven't done a concrete example yet. All right, we have not done a concrete example. All right, so we get to our first test, our very first test, right? We've got this sheet of tests, right? This list of tests that we're going to do. The very first test, and I'll go back to that sheet in a second. The very first test on that sheet is called the test for divergence. The test for divergence. So this test will only give you a result for divergence. Let me try and illustrate this in a different manner. Let's say I give you a test for COVID, right? That test does not test you for the flu, right? Is that obvious? A COVID test is not going to tell you if you have the flu. But more than that, this test for divergence, it only tells you if you're divergent. It only tells you if you're divergent. So it's almost like a COVID test that will only tell you if you're positive. But if it doesn't tell you you're positive, if it doesn't tell you you're positive, it doesn't mean that you're negative. Okay, it's going to be confusing. Let me just get to it, all right? Test for divergence. Given a series, okay? Given a series, it is very challenging to show whether or not it converges or diverges. I've already said that. It's very hard to do. However, for certain series, we can do a quick check for divergence. And here's the theorem. Given a series, if the formula inside, which is the sequence, if that limit of the sequence goes to something other than 0, then the series diverges. let's do an example. Okay, I'll put that back up in a minute. Okay, I'm going to give you a series. Ready? Does this converge or diverge? I'm just going to put from now on C and D because I don't want to write this over and over. Does this converge or diverge? I want us to take the sum. Shit. I want us, come on, man. What's going on? Stop. Okay, I want us to take the sum n equals 1 to infinity of n plus 1 over n plus 2. Now, that's the question, okay? Just to give you an idea of what I'm doing here, this means we're taking, let's plug in 1 first. We plug in 1 and we get 2 on top, and on the bottom we get 3, right? 2/3. Plus, now let's plug in 2. So now we get a 3 on top and a 4 on the bottom. And then plus, and now we get a 4 on top and a 5 on the bottom. And I'm going to keep doing this forever and ever, right? Forever and ever. And the question is, does that converge or diverge? So if I keep adding these forever, is that number going to become infinitely big, or is it going to go to a finite number, right? That's the question.
It's going to 1.
What's going to 1?
The sequence, not the
The
series.
sequence. Okay, so
Yes.
let's be real careful, everyone. Okay, what we're going to do, we're trying to figure out what the sum is doing, right? The sum is doing. So we are going to first look at the sequence, all right? The sequence that we're adding up, that's a sub n. And we're going to take its limit. This is what you did last class in chapter 8, section 1. I gave you a sequence and asked you for the limit. I want us to take this limit as n goes to infinity of this, n plus 1 over n plus 2. If you do that, you're going to get infinity over infinity, right? Infinity over infinity. So you would have to do L'Hopital and all that, right? I'm not going to go through that work, but hopefully L'Hopital on the top and bottom one time, you would get like 1 over 1, right? So this right here, this limit is 1, isn't it? So I want to know what the series is doing, right? What's the series doing? And so we looked at the sequence that we're adding up, and we took its limit, and we got a number that was not 0, right? That number was not 0. And the test for divergence says, if you get a number that's not 0, this series diverges. It says, given a series, right? If you look at the limit of the sequence and you get something that's not 0, then the series diverges and you are done. All right. This is a divergent series. So I'm going to say now, oh, by the way, this test is actually called, did I have it there in my notes? Why don't I have the name of it? Not sure why I don't have, here, I'll add it right here. This is called the Nth Term Test. It's called the Nth Term Test. So let me go to those, the sheet, right? The very first thing on this cheat sheet is the Nth Term Test. And it says, start with the series, okay? There's your series. Look at that piece inside, take its limit. If you get something other than 0, it diverges. It meaning the series diverges. The sequence converged, right? In the problem we just did, didn't the sequence converge to 1? But this is telling us the series diverged. Now, there's a comment on the side here. If the limit is 0, the test is inconclusive. I will illustrate that in an example. All right.
So it could still diverge even if you're going to 0.
Yes.
Okay.
Yes, I'm going to show you. Okay, so for this, let me finish it up. So I'm gonna say here, by the nth term test, the series, this series diverges. Okay, that's it.
But if
Careful.
it was less than 0 or 0, then
Well,
it would, then we don't know. We just don't
then
know.
we don't know,
it.
yeah.
Okay.
Yeah, so what if we took this limit and the limit came out to be 1/1000, 1/1000? We'd still diverge. Okay, we'd still diverge. It just, if it's not 0, it diverges. Right? So careful. Let's do another one. What about this? Sum n equals 1 to infinity of 1/n. So again, to kind of get an idea of what's happening here, we're going to take plug in 1, we get 1 plus. Now we plug in 2, we get 1/2, and then we get 1/3, and then 1/4. And so the question is, what happens here, right? Does this add up to be finite or infinite? I mean, finite or not? Is it finite or is it diverge? What the hell's happening? So I'm going to try the nth term test now. Ready? Nth term. I'm letting you know I'm about to do the nth term test. Here it comes. I'm going to take the limit as n goes to infinity of the sequence that I'm using, right? 1/n. So I'm just taking that formula right there. I'm taking the limit as n goes to infinity, and I'm going to get what here? 0, right? And what does the nth term test tell us? Hold on, don't reply. The sequence is going to 0, right? What is the series doing, right? That's the question. What is the series doing? So let me see. I want to ask somebody, but I'm not sure who to ask first. So I'll ask Caitlin first. We'll just go across my screen here. Caitlin, what do you think? I'm going to put the test up for you. We just ran the nth term test, right?
Yeah,
And we took the limit, and the limit came out to be what?
0.
Okay, so according to this test, what is happening? We got 0, right? When we took that limit.
Yep,
So the test is what?
inconclusive.
Inconclusive. This is like a faulty test, in other words. It's like a defective test at this point. We don't know if it's convergent or divergent, or we don't know. It could be divergent and it could be convergent. It's just this test is no longer valid. All right. So in a problem like this, we would then say test fails. All right. Or you could say test is inconclusive, however you want to say it. And then what you would need to do is move on to the next test, whatever that test is. Okay, ... We aren't going to do it because we're only talking about this one right now. So the way series are going to work is that I'm going to give you a series and you're going to go and try and do things to it. And you're going to, I'm going to try this test. And then you go, oh, you know what? This test isn't working. I better try a different test. And they'd be like, oh, that test doesn't work either. Oh, and they'll try this test. So it's a lot like when you were doing integration and you're like, oh, is this integration by parts? Is this a trig sub? Is this basic U sub? It's kind of the same sort of principle that there's not like a cookie cutter way of doing the problems. You're going to have to analyze the series. in the sequence. Okay, the biggest mistake I see students make on a problem like this one right here is they will say, take the limit 1 over n goes to 0, and they will tell me that the series converges. That's what they'll tell me. And it's wrong, right? It's wrong. Okay, let's do another one. Let's do this one. Sum n equals 1 to infinity of cosine of 1 over n minus 1 over n. No, minus 1. There we go. All right, does this converge or does it diverge? All right. So let's see here. Miyake, you're up. So what do you think? What are we gonna do here? Do you want me, let me write out a few terms first. So if I plug in 1, I get cosine of 1 minus 1, right? But then I say plus, now I plug in 2, so I get cosine of a half minus 1. Let me do one more. Then I have cosine of a third minus 1. This is just so you can see what's going on. So Miyake, what should we do? We're trying to figure out if this converges or diverges. Can't hear you. I see you talking, but I can't hear.
I think it diverges.
How?
Mm,
Well, what do we need to do? I mean,
I also think it diverges because if you have, and I mean I could be wrong, but even if you went, down fractionally. Oh wait, hold on, wait a second. I changed my mind. I think it converges.
my question to Miyake is, what do we need to do?
mm,
What do we do in the previous one? What test
Oh,
are we?
we looked at the little formula thing,
Wait, what?
right? Oh, I thought we went based off the summary of convergence and divergence tests for series, right?
Okay, so look, if we were sitting in a classroom, right? And I appreciate, Miyake, that you have your camera on, because at least I know you're there. All right, but if we were sitting in a classroom and you were holding a conversation with somebody else the whole time I was talking, then I would call you out in class and I would tell you, hey, either pay attention or leave. Okay. So I'm calling on you because I'm really trying to understand, are you following what we're doing here? If you're talking to someone else, or are you not? And again, you have your camera on, so at least you're doing that. There are some people who don't. But I'm here to try and help y'all learn. So you have to pay attention to what I'm doing. I mean, this is the next step. We only have one step at this point. We only have one step. I've only shown you one thing to do at this point, right? There's only one thing. So help out, whoever wants to help. What are we going to do?
Take the
Gonna
limit of
set
the
the limit.
sequence.
Take the limit of the
Sequence.
sequence. Okay, we're going to take the limit of the sequence. Let's do that. Here's the sequence. We're going to take the limit. Oh, sorry, we're running the Nth term test. I'm letting you know that so that you know what I'm doing. And when you're doing your work on your test, you should let me know what you're doing. Nth term test. Because there's going to be like 10 tests, and I'd like to know what you're doing because then it's easier for me to follow it. You're going to take the limit as n goes to infinity of cosine of 1 over n minus 1. Okay, let n go to infinity. 1 over infinity goes to 0, right? Cosine of 0 is 1.
1,
And 1 minus 1 is 0.
0.
Okay, according to the nth term test, if you do this, all right, if you do this and get 0, what?
It's inconclusive.
Brandon, we couldn't hear you. Sorry. I saw you talk, Brandon, but I couldn't hear anything. Jonathan, what'd you say?
I said it's inconclusive.
Inconclusive. Okay, so we've gained, we know nothing. At this point, we know absolutely nothing. All right, test fails. All right, and now we have to do a different test, which I have not shown you any other tests. I'm just really trying to stress to you right now that when you're looking at a series, if in the beginning you do get it to go to something other than 0, you're done and you're like, thank you, okay? Because that's super quick and it's relatively easy to do. But if you get 0, well, then you got a whole new ball game. You got you got to go through a bunch of other stuff, okay? But you don't want to overlook this because sometimes a series can be very easy to do, but you get so bogged down. It's like, when you've done an integral and you're like trying to do like integration by parts, and then you look back at it later, you're like, oh shit, that was just a basic U sub. This is kind of like the same idea. It's like you don't want to forget the nth term test because it's very, very powerful if it goes to something other than 0. It only sucks when it goes to 0 because then it's useless. All right. Okay, let's move on. I even say it here, students that make the mistake of thinking this theorem says that if the limit of the sequence does go to 0, that it converges, which is wrong. It is test for divergence only. Right? That's what I was trying to say when it's like we're taking a COVID test that only tells you if you're positive. But if the mark doesn't show up, then you don't know if you're positive or negative. Does that kind of make sense? So it's not like it's not like positive or negative. It's either positive or you don't know. That's basically what this test is.
It'd be like it's a test to see if you're sick, but it only tells you if you're not sick, but doesn't tell you what you're sick with.
Yeah, you could say that. Yeah. Okay, examples. Let me see. These were some examples. I think I've done enough examples. So, all right. Now, when it comes to series, all right, there's all kinds of series, just like there were with integrals, right? There's all types of things that we can try and find the antiderivative of. But when it comes to series, there's certain series that are just very important that all kind of look the same way, have the same behavior, kind of like when you talk about functions, you have like quadratic functions and you have like polynomial functions and rational functions. When it comes to series, there's a certain series that we like, that we see a lot in the real world, and they are called geometric series. And that's the first kind of special series we're going to look at, all right? So let's take a look at a geometric, or our first kind of introduction to it. Let me write what this is a geometric series, a specific one, all right? Geometric series are very general, but here's a specific one. So let me show you what it is. I'm doing sum n equals 1 to infinity of 1/2 to the nth power. All right, so let's write out what this is. First, we plug in 1, so we get 1/2, right? 1/2 plus, because we're doing the series. Now you do 1/2 squared, which would give you 1/4, plus then 1/8, plus 1, where are we, 16, plus 1/32, plus forever and ever, right? That's what the series looks like. The question is, does it converge or diverge? So what happens to the sequence? Let's look at the sequence. Let's look at the sequence. If I were to do the limit as n goes to infinity of this, of 1/2 to the n, we talked about this last time. This is a sequence that looks like r to the n. Do I need to bring up my notes, or do I, from last time? I won't. This, we know what this does. It depends on what r is. If this number in here is smaller than 1, this goes where?
To 0.
0, right? Okay, this goes to 0. If n is, I mean, if the number inside here is 1, it goes to 1. And if it's bigger than 1, it goes to infinity. It diverges. So I know that this limit goes to 0, right? The sequence, the limit of the sequence goes to 0. And means I've got a failed nth term test, right? So I know nothing. I know nothing about the series at this point, right? So this is like the nth term that I'm doing there. Golly. What the? Okay, nth term. The nth term is telling me nothing because it fails. All right. So we don't know anything right now. We don't know if it converges or diverges. All right. Okay, fine. Let's take a look at it. I want to show you this visually. Okay. I want to show you this visually. So what I'm doing here is I'm going to give you a visual representation of adding these things up. So here's a 1 by 1 square. I'm first going to add half of this square. Okay, so that's a half, right? Everyone agrees that's half. If it's 1 by 1 square, that's half. Okay, I'm going to add to that 1/4, which would be half of that half, wouldn't it? Which would be that piece. And now I'm going to add half of that, which would be that piece. And then half of that, which would be that piece. And half of that, which would be that piece. And then that piece, and 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 that piece. And I'm going to do that forever. Do you all see that this is going to converge to 1? Brandon, did you have a question? We don't hear you. Yeah, sorry. You can put in the chat if you want, if it's an easy thing to state. Do you all see that it looks like visually, this is not the golden ratio. I know what you're talking about. This is not it though. Do y'all agree that visually it looks like if you do a half plus a fourth plus an eighth plus a 16th, that you just like fill in this square, but you're never going to go outside this square. So like the area of this square is really representing what it means to add these numbers up forever. So it looks convergent, doesn't it? It looks convergent. But I need to somehow prove this to you. I can't just say it looks this way. And we need to do it generally. We need to do it, you know, what if this was 1/3 to the n? Or what if it was 1/4 to the n? It's a different picture. So this was just to get us thinking and trying to motivate the idea and hopefully convince you that, that it works. What else? I forgot, I did more of this. Hold on, did I zoom in? Oh, never mind. I'm having it add up. I'm having it add up for me, the computer, and y'all see what it's adding up to be right now? 0.999999, right? And I can have it go out much further. I'm just going to keep going. Okay.
Just turned into 1 after a bit.
It did because I have the computer rounding to 20 decimal places. I'll have it go out 40 decimal places, still 1, 75 decimal places. Okay. So see, it's still not quite 1, right? The further I go out though, the closer and closer. Let me back it up. Let me go all the way back here to when we had like just the first few, right? Just the first few added up together, 0.75. But the more I add, watch these 9s start to appear, 0.9999. It's just starting to fill in from left to right with 9s, isn't it? The further I go, the closer and closer this answer gets to 1. Will I ever get to 1? No.
No.
But in the limit, it's approaching 1. Do y'all see that? It's approaching 1. If I could go to infinity, it would be 1, but I mean, I can't. It's infinite sum, right? Okay, so the idea again is just that with this new thing called the geometric series, it looks like we do have some convergence perhaps, right? So what is a geometric series? What does a geometric series look like? A geometric series is any series of the following form. sum n equals 1 to infinity, some number a times r raised to the n minus 1. So up to this point, I'm going to copy this and move over to a different page. Up to this point, okay, up to this point, the series that we've been talking about have been just a generic, this in yellow, the sequence formula has been just generic, right? It can be anything. What I'm saying is, to be a geometric series, the formula on the inside must look exactly like this. Exactly. Has to be a number in front of r raised to the n minus 1. And let's just, if we start plugging in values, we can see this. Let's see. Let's plug in 1. If you plug in 1 for n, 1 minus 1 is 0. R to the 0 is 1. And 1 times a is a. And then you plug in 2. So 2 minus 1, that would give you 1. And then you'd have r to the first power times a, that would be a times r. And then you plug in 3. 3 minus 1 is 2. So you get AR squared. Do y'all see how this, where this comes from? This right here, A times AR times AR squared.
The one we just did as our example doesn't match that formula though.
It does, it's tweaked a little bit.
Okay.
It doesn't look like it, but it is.
It doesn't have the n minus 1 is the thing that's throwing me off.
It does, it's just hidden. I'll show it to you.
Oh, no.
Yeah, don't worry, it's hidden, but
I hate when you say that.
yeah,
It's just hidden somewhere. But
yeah, we're gonna have to see a lot of hidden stuff in this. So yeah, just hang tight. It's happening. Okay, so all geometric series look like this, right? All geometric series look like this. So let's just kind of back up. If I want to know what this series is doing, then I have to create a new sequence. The new sequence is the partial sums. So what is S sub 1? That would just be the first guy added up, right? Which would just be A. What would S sub 2 be? Well, that would be A plus AR. What would S sub 3 be? Well, that'd be A plus AR squared. Yes? And S sub 4 would be A plus AR squared plus AR cubed, right? And so what would the S sub n be? What would the formula for S sub n be? Well, A plus AR squared, right? Plus ... all the way till I get to the very last one. I'm stopping at n, right? So if I stop at n, where would I be? Be real careful here. When we plug in 4, we stopped at AR cubed. If we plug in 3, we stopped at AR squared. So if we stop at n, will be AR to
AR n minus 1.
n minus 1. Y'all okay with that?
What
What I
about
really-
what about ARN? Is that before ARN minus 1?
AR to the n would be after this one,
Oh, okay.
right? But we're stopping here. We're stopping it. Of course, when we go to infinity, it goes on forever. So we don't have a stopping point. But I'm looking at this sequence. And remember, what we're trying to do is this. We're trying to figure out, can we do the limit as n goes to infinity of S sub n? If we can do this, right? If we can do this, if we can take this limit, then if we get an answer, this answer is our sum, okay? If we can take the limit as n goes to infinity of this formula right here, not this one, please don't, we're not talking about this anymore. We're talking about this one, right? That if we can take that limit, let n go to infinity and get a number as an answer, that will be the sum, okay? That'll be the answer. But there's a problem. If I try and take the limit as n goes to infinity of S sub n right now, this is S sub n, isn't it? That's what S sub n is. What is wrong with me letting n go to infinity on this? What does it do? Doesn't n go to infinity make this longer?
Yeah,
Right? The dot, dot, dot means that this thing goes until I get to n minus 1, right? That's the very last one, n minus 1. So if I let n go to infinity, it's going to make this sum longer, isn't it? It's just going to make it grow and grow. That's not, we can't tell what that's doing because it's just making the sum longer. So this is right now huge, huge problem. We don't know how to handle this, right? Like we have no idea how to handle that.
I'm not getting how it makes it longer. How does it make it longer? Because
Okay, well, look at this one. Look at S sub 1. How many numbers were in S sub 1 that we were adding up? 1. How about S sub 2? 2 of them, right? S sub 3, there's 3 of them. S sub 4, 4 of them, right? S sub 100 would be 100 of them. So S sub n would be, we would have 100 of these. I mean, sorry, there are n things being added up together here, right? 1, 2, 3, all the way to the last one. So if I let n go to infinity, how many are you adding up, Louis? Infinite, right? Infinite. So it's the dot, dot, dot right
infinity,
here.
right?
I'm sorry?
It would be n plus infinity.
N plus infinity.
So the number we choose plus the infinity because n minus 1, n minus 2.
I'm just talking about the number of terms you see in there, right? The
Yes, sir.
bigger n gets, the more terms you have. So if I try and let n go to infinity, I'm going to have an infinite number of terms, which I can't add up. I don't know how to add that up. See, there's a big difference between taking the limit of this and taking the limit of this, right? If I just take the 1 over n right here and take the limit, let n go to infinity, I only have one thing that, you know, the n's going to infinity, fixed over infinity, that goes to 0. I'm not having to like make it grow by letting n go to infinity. I'm not adding up more things. There's only one expression I'm looking at. Does that kind of make sense?
No, but I'll get you after class.
Okay. Okay, so we have a huge problem, right? We have a huge problem. Now the brilliance. You ready to see brilliance? This is not me. Someone else figured this shit out. You ready? So this is what we're struggling with. We have this. We have this. We'd really, really like to know what this is, right? But we can't do it because when we try, it makes this sum get really big. Big as in longer, which we can't do. So here comes the brilliance. Don't ask why I'm doing this, just follow me with it, all right? What I'm gonna do first is I'm gonna take that S sub n and I'd like for you to multiply it by n. Okay, so take what's in that black box, multiply both sides of that equation by n. Sorry, not n, r. Sorry, by r. Okay, so do that on the left and right. Okay, on the right-hand side, if I multiply every one of these by r, I will get AR, right? That A now has an R next to it. The next one will be AR squared because now I've added another R to this one. The next one will become AR cubed plus dot, dot, dot. Okay, what would happen to this one? What would this one become?
wouldn't it just be AR to the nth?
AR to the n, right? Does everyone agree with that? Because you're multiplying this by R. So that's r to the first power. You add these two exponents together, you get n minus 1 plus 1, right? N minus 1 plus 1 would just be AR to the n. Now watch what I do. I'm going to do AR to the n. That would be the last one now, wouldn't it? That's what it is. But the one right in front of it, I left a space for it because I wanted to just make sure you saw it. The one right before this one would be AR to the n minus 1. It would be there, right? It would be there. Okay, that's the first part of this. Ready for the next part? What I'd like for you now to do is I'd like for you to tell me what S sub n, okay, I'm going to just separate idea kind of. I want to know what S sub n minus R times S sub n would be. Why? What are you doing, Robert? Okay, so I want you to take this row, S sub n, and subtract this row. So
Don't you-
what would happen to these? Look at what happens. You do A, you're gonna take away each of these. So do y'all see that this AR, you're gonna take that one away, it would go away? This AR squared would go away with this one. The AR cubed would cancel that one out. Y'all following me? All the way down the line till you get to this one would cancel this one out, right? What's still here? What is still here?
A plus AR to the nth.
A, that one was on top, so we have that A there, right? We have A there. But we are subtracting this row, so wouldn't this be minus, right? Minus AR to the n? Right, if I take this top row and I subtract this bottom row, the ARs go, the AR squares, AR cubes, this A is still there. And then this AR to the end never got subtracted from anything, so it's stuck at the end also. Do y'all see that algebraically or not? Yes, no? Yes. Okay. It's where we are, right? Check this out. On the left side, I'm going to factor out an S sub n because they both have S sub n in them. I'm left with 1 minus R when I do that. And this is A minus AR to the n. Y'all still there? Divide both sides by 1 minus R. Factor out an A from the top. Does anybody see what we've just done? Think about what S sub n used to be. Think about what S sub n is now. In the first formula for S sub n, I had a dot, dot, dot in there, right? Which meant that I was adding and I was stopping at some point, right? In this new formula for S sub n, which we got through this crazy algebra that you would have never come up with on your own. Through this crazy algebra, I have a new formula for S sub n, and do you see any dot, dot, dots here? So as n gets bigger, I don't have more things to add up. I just have to figure out what happens to that as n gets big.
So is this like the true formula for S of n, like in terms of that?
For a
function?
geometric series, this is the formula for S sub n, for a geometric series. It has to be a geometric series for this to work. So now let me ask you this question. If we take this and we take the limit as n goes to infinity of this, right? A 1 minus r to the n over 1 minus r, isn't n only appearing in one place right there? So I basically have the number r being raised to the n, and I'm letting n go to infinity. What happens to r to the n as n goes to infinity? Well, doesn't it depend on r?
Yeah, if it's less than 1, it goes to 0. If it's 1, it goes to 1. And if it is higher, then it goes to infinity.
Yeah, so let me jot that down. If I take the limit as n goes to infinity of r to the n, this has 3 different scenarios. If the absolute value of r is less than 1, this thing goes to 0. If the absolute value of r is bigger than 1, it diverges. And if r is 1, or the absolute value of r is 1, then the answer is 1. So doesn't that mean that this limit that we're taking right now for this expression up here for S sub n, it has some possible different scenarios, doesn't it? So here are the scenarios that can happen. You tell me, if the absolute value of r is less than 1, Okay, if the absolute value of r is less than 1, we know that that r to the n is going to go to 0. Okay, so imagine what would happen if this r to the n went to 0. We would get 1 minus 0, which is 1, times a over 1 minus r. Right, so wouldn't it just be a over 1 minus r? And then what if the absolute value of r is bigger than 1? Well, if the absolute value is bigger than 1, this is going to diverge. This thing's going to become infinite, which means this whole ratio is going to blow up and become infinite, right? Which would mean that this thing diverges. And what if r is 1?
And it just 0 then? Because your ones kill each other off there and it's multiplying by 0.
You would basically get 0, right? You get 0 here. Right? Which would give you what? Convergence or divergence?
Converge to 0, wouldn't
Converge
it?
to 0, right? Okay. Now, believe it or not, this is a pretty big deal. I want to go back to the sheet again. All right. The big thing here is geometric series. All geometric series look like this. If the absolute value of r is less than 1, we will get convergence. If the absolute value of r is bigger than or equal to 1, we will get divergence. That's it. That's the conclusion. So let me show you the example that, to follow this up so we can have something rock solid to go off of. All right, so let's look at this example. Let's say we take a half plus a fourth plus an eighth plus a 16th plus forever, right? I want to know what this is. Does this converge or diverge? Right? This is the one with the squares we just did, right? Half a square, a fourth a square. I filled it in and we said this should go to 1, right? That's what we said. This should go to 1. Let's prove it goes to 1. So the first thing I'm going to notice on this is that this looks like the sum n equals 1 to infinity of 1/2 to the nth power. Okay, do y'all agree with that? That's what that is. And I sit there and I go, wait a minute, hold on. That looks like a geometric series. Here's what geometric looks like. A r to the n minus 1, right? That's geometric. And I know that I can determine whether or not it converges or diverges. It all depends on r, right? It all depends on r. The problem with what we see here in red is what Hunter pointed out earlier, is that this does not match this formula exactly. There's something, it's similar, but it's not exactly the same, is it? This has a number in front, r raised to the n minus 1. Do we have an n minus 1? No. Do we have a number in front right now?
1.
A 1. We could say there's a 1 in front, right? We could, but we don't have an n minus 1, do we? Not yet. Not yet. So now I'm just going to be clever. I want an n minus 1, right? I have an n, I want an n minus 1. So what am I going to do? I'm going to write n minus 1 plus 1. It's all right, Lewis. So we did some of this, we've done some of this before. And the reason I did it before is because I wanted you to have this sort of mental idea when we got to this, whole idea of, subtracting and adding something. It's important here in this section quite a bit, or in the next few sections. So now what is this? This is just sum n equals 1 to infinity. This is really just 1/2 to the n minus 1 times 1/2 to the 1. So now I've just split it apart, right? And now that 1/2 to the 1, I'm going to write that as a 1/2 in front, and then the 1/2 to the n minus 1 behind it. I'm just doing that so it'll look exactly like this geometric. And do y'all see it now? A r to the n minus 1. Now that's geometric. I know that A is 1/2, and I know that R is also a 1/2, right? And so I go to my little cheat sheet and I say, okay, what happens? How do we get convergence? I need the absolute value of R to be less than 1. Well, if I take this and I take the absolute value of it, of course, I don't need to because it's already positive, but that would be a 1/2. And that's definitely less than 1, right? Which means we have convergence, right? We have convergence. So I know that this converges. But even more than that, I know what it converges to, because it says here it converges with the sum S equals A over 1 minus R. So I know what it goes to. This goes to S equals what? A, let me write the formula. It's A over 1 minus R, right? That's the formula. So A here is a 1/2 over 1 minus R, which is a 1/2. And that's going to be 1/2 over, well, 1 minus a 1/2 is a 1/2, and a 1/2 over a 1/2 is 1. So that geometric series converges to 1. We got our first geometric series. Now, what if this would have been 4/3 to the n minus 1? What if this number right here would have been 4/3 to the n minus 1?
4/3?
It would diverge.
Yeah,
right?
then it would just diverge.
It would diverge and you'd be done. So the whole key to a geometric series is to figure out, rewrite it in a way that it looks like this. Okay.
We don't have to tell you what direction it diverges from negative infinity to infinity, or
No, because divergence just means not convergence. That's all it means. Okay. Convergence means it's going to a number. Divergence means it's not. It doesn't
Oh, yeah, 'cause
necessarily
it's-
mean it's going to infinity.
yeah, because the series is like movable.
Yeah, it could be like a good example of that is if I asked you to do this sum. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 forever. That series is actually divergent. It doesn't head to a number, and it doesn't head to infinity either, or negative infinity. I'll get back to that one. I want to do one more example before we have to call it a day. I'm not done with this section. All right, I'm going to need more time. Okay, so here's a really, really crazy problem. All right, it's not crazy, it's just weird. Okay, it's weird. So look at this number. 0.1575757 forever. So it's repeating the 57. Be careful, there's a 1 in front here. 0.1, then 57575757. Here's what I want you to do. I want you to write this as a fraction. Write it as a fraction. In other words, there's a fraction that when I type that into my calculator, hit enter, it's going to give me 0.157575757. But I would like to know the fraction that you have to type into your calculator. Okay. How is this related to geometric series, right? Like, how in the world is this related to a geometric series? You ready? Here we go. Do you agree with this? This is 0.1 plus 0.057 plus 0.00057 plus 0.0000057. I'll do one more. Plus 0.000000057 plus forever. Y'all see what I'm doing there? 0.1, I just got that one out front, 0.1. And then if I added these two together, right? Because I put a 0 in front of the 5, 7, I add those two together, I get the first three numbers. Then if I do those together with this, I would get the first three plus the next two. And I keep doing that forever. Do y'all buy that? Yes. Okay, isn't this equal to, well, 0.1 means 1/10, right? 0.1 plus, okay, that's 0.057. Doesn't that mean 57 over, what position is this? Tenths, hundredths, thousandths. So isn't this over 1,000? Right? Plus, okay, 57 over, what position are we in? Tenths, hundredths, thousandths, 10,000ths, 100,000ths. Plus, okay, I'm starting to see a pattern here. Aren't I just adding 2 zeros on the bottom each time? Right, because I'm going 2 decimal places. So 1 0 0 0 0. How many? I'm going to need 7 zeros. Wait.
Can't you do this for any decimal? You just add, it's just divergent or convergent, like.
Well, this is a repeating decimal, right?
Yeah, but like that decimals that aren't convergent or like that are sporadic, like we said. So for example, you can go 1/10, and then let's say this is just 0.1 3 4 7 3 4 5 6 whatever.
Yes.
Then you would,
Mhm.
and then we can just say it's just divergent, like it doesn't matter. Does it make sense? So you put the limit in terms of, like, so for example, 1 minus 1 plus 1 minus 1, those don't really go to anything. The same thing as the decimals that are irrational, like pi or something. They don't go to a number, so therefore they're divergent, question mark.
Okay. I think, I'm not sure if I'm following your question. I'm giving you a number, right? That is a repeating decimal. Okay. So it's not irrational, meaning that like pi and square root of 2 and e, those are numbers, decimals that go forever and ever, but never have a repeating pattern. Never, right? That's what irrational means. What I'm showing you right now is that if I give you any decimal that repeats, that has a pattern to it, I can always start to rewrite it this way, right? Okay, let me continue. This is definitely, let me continue because we can't talk about divergence here. This is a number. I mean, it's a finite number, right? So I shouldn't have an idea of divergence with just if I give you a number. I'm trying to get this converted to a fraction, and you're trying to demonstrate that we are going to see, hopefully, that we're going to get a geometric series out of this. So let me do one more of these. How many zeros should I have here? 9, right? This is 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I keep going. Yes? Is that all right? But this is just 1/10. Now watch this. This is the part that's cool. I'm going to start, I'm kind of ignoring the 1/10, and I'm noticing that all the others have a pattern to them. This is 57 over 10 to the 3rd power, right? That's what 1,000 is. Plus, this is 57 over 10 to the 5th power, because I have 5 zeros, plus 57 over 10 to the 7th power, plus 57 over 10 to the 9th power. And that keeps going, right? Next one would be 57 over 10 to the 11th. Focus all of your attention on just the yellow piece right now. Okay, it goes forever. Focus all your attention there. Bring the 1/10 down. And then say plus everything in yellow. Agree or disagree? Sum n equals 1 to infinity. Okay, I notice all of these have a 57 on top. And the bottoms are 10 to powers, right? 10 to the third, 10 to the fifth, 10 to the seventh, 10 to the ninth. Hey, the only thing changing there is the power. They're just the odd numbers starting at 3. How do you create the odd number starting at 3? What's the formula you would use to create the odd numbers at 3?
2n minus 1 or 2n plus 1.
2n plus 1. 2n plus 1, right? Would create the powers. I mean, would create the odd number starting at 3. So couldn't I put down here 10 raised to the 2n plus 3? Sorry, 2n plus 1. I could do that, yes. Okay, more magic. Let me go. I only have 8 minutes. More magic. This is 110 plus. Okay, I'm going to show now this is geometric. I'm going to massage this. You ready? I'm going to have to massage it quite a bit. First thing I'm going to do is I'm going to pull the 57 out front. And then watch the way I leave the rest of this. Because if I pull the 57 out front, I have this over here. Right, that's what I would have 57 in front of that, like that. I'm going to rewrite that like this. 1 over 10. Well, you know what? Let me not, I won't go that far. I'll go 1 over, let me just put it here. 1 over 10 to the 2n plus 1. All right, forget this. And what am I trying to get at? I'm trying to get it to look like this. Right? That's what I'm trying to get it to look like. That's geometric. Okay. How am I going to do this? So I'm going to do the following. You just tell me whether or not you agree with this or not, all right? Is this not 10 to the 2n times 10 to the first power? Isn't that what 10 to the 2n plus 1 means? Right? Okay, I'm going to cheat. But doesn't that just mean I can take that out and put it out front with this 57 and make that a 57 over 10? In other words, just take this 10 to the first power and just pop it out underneath this 57. Right? That fair? Now, this is the first time you're seeing this. So if you're like, how would I ever think to do that? I understand. You just, that's why you're here, okay, to watch this happen. So now watch the way I write 10 to the 2n. I'm going to write it as 10 squared to the n. That's the same thing, isn't it? But isn't 10 squared 100? So now I have this. That okay? You'll see where I'm going here well, hopefully real soon you'll see where this is headed. Okay, now I'm going to rewrite this whole fraction. I'm going to rewrite it like this. 1 over 100 to the n. Because putting an n on the fraction 1 over 100, the n would be applied to both the numerator and denominator, but 1 to any power is just 1. So this is a legal move.
Wouldn't it be negative n since it's underneath? And we're taking it in terms
I'm
of,
not bringing the 100 up though. I'm leaving it as 1 over 100. So the n would be applied to the top and the bottom, which would give you 1 to the n. So basically that's 1 to the n over 100 to the n. But 1 to any power, like I said, is 1. So that's 1 over 100 to the n. Am I almost there? I'm looking for a number in front and then some number being raised to the n minus 1. I've got a number being raised to the n, not n minus 1. So I need what now?
plus minus.
Yeah, I need to subtract and add the 1. Okay. How are we doing on time? Okay, so now here I come in, I do -1 + 1. Right there. Okay, when I do that, I can split this off now and I can put a 1/100 here to the first power, right? Splitting that up. And then bring this 1/100 right here underneath the 57 with the 10. So here's where I am. I've got 110 plus sum n equals 1 to 100, I mean 1 to infinity of 57 over 1,000, right? 57 over 1,000. And now I have the 1/100 to the n-1, and that is geometric. That's geometric. I have A and I have R. And is the absolute value of R less than 1? Yeah, right. So this converges, right? R is 1/100. So definitely the absolute value of R is less than 1. Check. So what does it converge to? A over 1 minus R, right? That's what it converges to. So this is going to become 110 plus, okay, this whole thing is going to converge to A 57 over 1,000 over 1 minus R, but R is 1/100. Come on, we can do it. We got like 1.5 minutes. This is going to be 1/10 plus 57 over 1,000 over 1 minus 1/100 is 99 over 100. I'm going to continue this over here. I want to fit this all on the one page. This is equal to 110 plus, okay, I'm going to just reciprocate that. That's 57 over 1,000 times 100 over 99. And I think I get some things to cancel out here. 100 goes into 100 once and 100 goes into 1,000 10 times. So 1/10 plus 57 over 990. 99 times 10 is 990. One more step. Common denominator between those two fractions. Let's put them together. Which means I'd have to multiply this first one by 99 on top and 99 on the bottom. Which would give me 99 plus the 57 over the 990. And what's 99 plus 57? 56 over 990. There you go.
Wait, hold on. I have a question. How did
Yeah.
you get 99 plus 57? How'd you get 56?
It wouldn't be 156.
Oh, 150. Oh, oops, I forgot the 1. Sorry about that. 156. All right, time to check our work.
I was about to say sequences are getting real weird.
Yeah, let's take on our calculators, take 156 and divide it by 990. Tell me what you get as a decimal.
1.57 repeating.
Yep, 1.57 repeating. All,
It also rounds down to some terrible number.
yeah, all repeating decimals can be written as fractions using this method. All repeating decimals can be rewritten as fractions using this. Anything that doesn't repeat and goes forever can never be represented as a fraction. That's why pi can't be represented as a fraction. That's why e can't be represented as a fraction, because there's no way to get it into a geometric series. Okay, I'm out of time. So homework wise, we have not done this whole section. So I'm going to just keep you kind of in the problems that you can handle right now. 7 through 12. So this is from 8.2, section 8.2, just try and do 7 through 12. The reason why, hold on. Yeah, see how it goes. See how numbers 7 through 12 go. Don't do anything else. If you're really ambitious, you can try 31 through 34. Those are all problems like I just did, where they give you a repeating decimal and they ask you to figure out the fraction for it.
All right, I have a question about the homework. We on Canvas, it says we have a thing of homework due for 2
Yeah.
sections we haven't even touched on yet.
Yeah, I've got to update those dates. Just stick with what we're doing here.
Do we
and,
turn
you know,
do we turn
submit
anything on it
what
or
you
just
can.
ignore it?
Ignore it.
Okay, cool. Thank
Ignore
you.
it. Okay, do your homework. Do what you can out of this, all right? Because we're going to get more into this next time. Have a good day, everyone.
Have a
Thank
great
you.
day.
Thank you.
Why is this thing not showing up?